Okay, so coming back to this problem, we want to know when is g prime increasing? Well, just this is the derivative of g of x. Just language-wise, we call this g prime of x. Gone over that before, but just as a reminder. So when is it increasing? In other words, let's just look at increasing. When is the slope getting more and more positive? That's what this is really asking. When g prime of x is increasing, what that's saying is when is the slope getting more and more positive? Well, it's getting more and more positive. Let's look. Here we're very negative, getting less negative. Here we're 0, positive, getting more positive. And so for this whole red section, our slope is it goes from negative to less negative to 0 to positive to more positive. And at this point, right here, it's the most positive. We're talking about the derivative. And then afterwards, our slope is getting less, equals 0, now it's negative, and now it's the most negative. So in this green section here, during that green section, my slope is decreasing. And at this point here, g prime of x is most negative. And then after that, we're very negative, less negative, 0, and now we get more and more positive. So I used these two different colors intentionally. On what intervals is g prime increasing? During the red intervals. And when is it decreasing? During the green intervals. Now, red and green are a great math language, but pictorially it helps. So what are those intervals? From negative infinity up into negative 1 and then including 1 to infinity. And it's decreasing from negative 1 to 1. Now, you should start thinking, oh, there's something going on here more than just the derivative increasing or decreasing. But what's true about the red sections versus the green sections? Well, in the red sections, what about the concavity? During the red sections, we are concave up. So in other words, when f prime of x is increasing, it's concave up. And similarly, when f prime of x is decreasing, our function, f of x, is concave down. And let me just add that here. When f prime of x was increasing, our function is concave up. Big distinction, and this won't click right away. It'll take a couple days to sort of to sift into your brain. But for now, see that. During this whole red section, as we go left to right, my slope is getting more and more and more positive. During the green section, it's getting more and more negative. And during the red section, it's getting more and more positive once again. And what we notice, the red section is concave up, green section concave down. And so we drew this connection, we drew this rule. If my derivative function is decreasing, my function is concave down. If my derivative function is increasing, my function is concave up. Okay, so now we need to sketch a graph of g of x. Well, let me pause for a second. Looking at, just starting over on this new page, so we know that for g prime of x, it's going to be 0 here, here, and here. And we know that because of we've got these local maxes and local mins. And, well, what else do we know? If we're looking at, here's the black is g of x. And if I want to know about g prime of x, let's look at the tangent lines. So at this point, where we should have the biggest g prime of x, because g prime of x is the slope of g of x. By inspection, what is that slope roughly? Well, it's roughly 1, so let's put 1. And here we've got the least slope, and that has a slope of roughly -1. Looking at drawing a tangent line and inspecting its slope, it's roughly -1. So in between, in this region here, we get a good picture of the graph. Start at 0, get to a max. And again, what I'm drawing here is the derivative function, just to be helpful. In black, we have g of x. In green, we have g prime of x. Okay, then, what happens when x is greater than 2 and less than 2? Well, we know that we're, looking at the function itself, for all of these values, g of x is decreasing. And for it to be decreasing, it means the slope is negative. So we get a negative slope. And for when x is greater than 2, we've got g of x is increasing, so it's a positive slope. And so in green here now, we've got a good picture of the derivative function. And we got that by A, looking at the critical points, which occurred at -2, 0, and 2. And then B, we looked at, the points of inflection, or in red, where our slope would be a max or a min to give us a frame of reference. And then we just connected the dots, looking at, when is g of x positive, or when is g of x increasing, which means that my derivative function should be positive. When is g of x decreasing, which means my derivative function should be negative. So this is some challenging work, but we're going to grapple with this for the next couple of days. So be patient with it. Maybe rewind, look at this again, look at the development of this. It's something that we'll spend a lot of time in the next couple of days going over. Now, just to make things a little bit even more tricky, now we're going to take a function. We're going to take g prime of x, and we want to get a picture of its of the actual function. So we have g prime of x, and what we're going to eventually want to do is sketch a possible graph of g of x. So first, let's answer these questions. On what intervals is g increasing? Well, we need to interpret these questions. For g to be increasing, that means g prime of x needs to be greater than 0. Well, where does that occur? All of these values in red, my derivative function is above the x-axis. It's positive. So where is it increasing? It's increasing from -infinity up until -3. Not including -3, because there it equals 0. From -3 to 2. And then from roughly 3.5 onwards to infinity. Notice that I'm using parentheses instead of brackets. The parentheses means not including those endpoints. So where would it be decreasing? Well, it's decreasing when f, or g prime of x, is less than 0, and so that's just on this range here. So from -2 to 3.5. Again, these are the x values. Where does g have critical points? Critical points are when g prime of x equals 0 or undefined. We haven't looked at the undefined case yet, but where's g prime of x equals 0? Here, here, and here. So there are critical points when x equals -3, 2, and 3.5. Where does g have a local max? So these questions are great review for the generalizations that we've made so far. So a local max occurs when our derivative function goes from positive to 0 to negative. So positive slope, 0 slope, negative slope results in my function having a local max. Where does that occur? Only here. The local max, and that local max is occurring when x equals 2. What about a local min? Local min, similarly, is when we have when my derivative function function goes negative, 0, positive. So in other words, my function has a min when the slope goes from negative to 0 to positive, and there we get our local min. So thinking about that in terms of my derivative function up here, here it's negative, 0, and then I've got a positive slope there. So it has a local min at x equals 3.5. So tying this all together so that we can get a graph of g, we know that there's a, let's see, g is going to be increasing on these intervals, and we did this before from negative 3 to 2 and 3.5 to infinity. We know that. We know that there's going to be critical points at negative 3, 2, and 3.5. So when x equals negative 3, 2, 3.5. We know that there's going to be a max at x equals 2, a min at x equals 3.5, and we got that by knowing we went positive, 0, negative, and then negative, 0, positive for looking at our derivative function. And then what we need to do is, so we have all that, and then it says g of 0 equals 1. So we know that on our function for g of x, it contains the point 0, 1. So we know we contain that point. Now let's kind of think about what's going on. So we also know that g prime of 0 equals 3 from this point, which means that the slope of g of x at 0 equals 3. So let's draw in a slope of 3 roughly, something like that. And then we know that we're going to have a local max at x equals 2. So at x equals 2, we're going to have a local max. So we're going to have something like that. And we're going to have a local min at x equals 3.5. So it's going to come down, go back up. And those are our only max and mins. And we know that when x equals negative 3, g prime of negative 3 equals 0. So it's going to flatten out for a second. So we're coming, negative 3 is 0. But afterwards, we still have a, for x being less than negative 3, g prime of x is greater than 0. So it still has a positive slope. So we're going to go down again. So looking at this graph, where is my function increasing? Well, it's increasing from negative infinity to 3, and then it equals 0, from 3 to 2, and then from 3.5 to negative infinity. So that we got that right. We have a max at x equals 2. There's our max. We have a min at x equals 3.5. There's our min. And then the last sort of big kind of chunk to look at is that right here, where our derivative was a max, we had a point of inflection. So drawing that in, it went from being concave up to concave down. And here where we had a local min, it went from being concave down to concave up. These are the idea of point of inflection and changing of concavity. That's for another day, but just wanted to kind of throw those hints out at you now so you start becoming familiar with that. This is a very hard thing, and students have a challenging time getting this right, and we will spend due process on this, and you will feel confident with this soon. I would recommend just trying one of these later, maybe rewind and look at this again, but we will spend a lot of time over the next